Okay, this is Kinetics and Gas Laws 3 as we're going on here. Here's your quiz. We're going to start right with a quiz tonight. Beginning with a pressure of 1 atmosphere and a temperature of 27 degrees. If the temperature is raised to 927 degrees, A, what is the name of the law? Remember, what's held constant? I'll give you a clue. B, what is the formula of the law? And C, what will the new pressure be? Go ahead and pause the video, answer the questions, and then come back. Okay, hopefully you've come back now. Go ahead and correct your own. Haha, you're home by yourself, so please be honest. Here we go. It is Gay-Lussac's law because volume is held constant. Volume is not mentioned. The formula is P1 divided by T1 equals P2 divided by T2. And if you work it out, you end up with 4 atmospheres. Whoops. So, give yourself 1 point for Gay-Lussac's, 1 point for formula, and 2 points for working it out. So a total of 4 points. Not a lot, but it's okay. Alright, so tonight we're going to worry more about the kinetic theory. Now, I call these the toddler rules, and I'll explain to you why after we explain each one. Okay, the kinetic theory basically has to do with how things bump around. Okay, so if you look in the boxes here, the molecules are colliding with each other and with the sides of the container. Bromine gas, you can see here, doing the same thing. So we have postulates for the molecular kinetic theory. And the postulates are, first, gases consist of tiny particles or atoms. Well, toddler, tiny. Okay, can sit on your lap, doesn't have to pay for a seat. Number 2, these particles are so small compared with the distances between them that the volume or size of the individual particles can be assumed to be negligible or 0. In other words, I don't have to pay for their seat. Okay. Number 3, the particles are in constant random motion, colliding with the walls of the container. These collisions with the walls cause the pressure exerted by all gases. Think of a toddler. They say, "Ooh, look at that," and they run straight towards it, and then they get distracted and say something else, and they run straight towards it, and then they get distracted and they run straight towards the other thing. They don't wander back and forth between all of them. They go straight to whatever they're looking at. Okay? And yes, sometimes they collide with walls or whatever's in the way. Number 4, these particles are assumed not to attract or repel each other. If you've ever watched a toddler, they'll go up and talk to anybody. Okay? They're everybody's friend. That is until they get stranger danger. Okay? Number 5, the average kinetic energy of a gas particles is directly proportional to the Kelvin temperature of the gas. Think of a toddler. If it's nice outside, they want to be outside, they want to be playing, they want to be going, go, go, go. If it's cold, they want to snuggle. Okay? So, kinetic energy, amount of energy, is directly related to the temperature. So let's make it simple. If I have an ideal gas, the particles in an ideal gas will have no volume. In other words, they're like the toddler. They can sit on your lap. They have elastic collisions. They just sort of bump off things, and unless anybody's looking, they don't cry. They keep going. So they just keep going. Are in constant random straight line motion. See something I want, I go to it. See something I want, I go to it. Toddler, toddler, toddler. They don't attract or repel each other. They're curious. They go up and say hi to everybody. Okay? They don't look at somebody and say, "Ooh, they look scary." They just go up and say, "Hi, how are you?" Okay. Next one, have an average kinetic energy that's related to the temperature. Again, warm outside, they play. Cold inside, they snuggle. Okay, so that was the toddler rules. Get real. These are teenage rules. Come on, really? Particles in a real gas have my own volume. I need my own space. And they are attracted or repelled from each other, right? Because as you get to a teenager, there's some kids that just sort of attract you, and there's others that you don't want to get near. But when is our real gases most like ideal? So when are teenagers most like ideal people? Well, that would be the summertime. Right, at low pressure, I don't have to worry about tests. And at high temperatures, oh, get my suntan. And when I'm not put into situations with people I don't want to be with. So I don't have to be in that classroom with Joe Schmo that I don't like or that's slobbering all over me. I can choose my situation. So this is to help you remember. Real gases, like a teenager. I have my own volume. I'm attracted and repelled. I didn't put repelled there, but it should be. Repelled by others. And when am I most ideal? In the summer. Low pressure, high temperature, and I can choose my own situation. So non-polar. Non-polar. All right, let's go on. So if I look at a collision of gas particles, elastic, bounce right back. Inelastic, sort of like a car crashing into a wall. Not real elastic. So let's talk about some characteristics of gases. Gases expand to fill any container. They're in random motion, no attraction. Okay? Gases are like fluids, or like our fluids. They're like a liquid. They'll flow. Okay? You can actually pour a gas. If you'll remember from our demonstrations that we did in November, when we poured the gas of that chemical down the ramp, and then the ramp caught fire. Do you remember that? Okay. That's because gases are like fluid. They will flow. They have no attraction. Gases have very low density, no volume, lots of empty space compared to the volume that they do take up. So solid, liquid, and gas, very far apart. Some of the characteristics of gases. Gases can be compressed. That's why we don't like them in our brake lines. If we can compress them, then that means the calipers are not going to close and make my brakes work. So if we got gas in the brake line, that's bad. Okay, no volume, lots of empty space. Gases undergo what we call diffusion and effusion. Diffusion is throughout a room, and effusion is through a hole. Okay, it's random motion. It just randomly goes there. So, kinetic law. Here we have original temperature, original pressure, original volume. If we increase the temperature, we increase the pressure, and we have the original volume. If we increase the temperature, original pressure, we have to increase the volume. So, these are our gas laws, guys. So if you remember the gas laws, you can get the kinetic theory. Here's another one. Volume and number of moles. Certain number of pressure, volume, moles 1. If I increase the volume and keep the same pressure, if I increase the number of moles. And then if I 3 times the volume, then I've got to 3 times the number of moles to get the pressure the same. Okay? Changing the size of the container. In smaller containers, molecules have less room to move. It's just like putting 40 in a class that was made for 20. There's not a lot of room to move. Okay, they hit the sides of the container more often. They bump into each other more often. They cause an increase in pressure. That is of the teacher. No, I'm just teasing. Okay, they cause an increase of pressure because they're hitting the wall more often. They're hitting each other more often. Okay, as the volume decreases, pressure will increase. So, here's a balloon riddle. We're going to do this in class actually, so you get to pick. What do you think? When the balloons are untied, so in here I'm going to have a valve. I've got a big balloon on one side, a little balloon on the other side. What do you think is going to happen? Is A going to happen? Or is B going to happen? Or is C going to happen? And why do you think? We're actually going to do this in class, so pick this now and let's see what you think and where you're going with that. Let's talk a little bit what's going on. You have pressure inside the balloon pushing out from the molecules hitting the outside. You also have pressure exerted on the balloon from the molecules that are in the air. Okay? When a balloon is being filled, the pressure inside is bigger than pressure outside. When a balloon is filled and tied, the pressure outside and inside are equal. When a balloon deflates, the pressure outside is bigger than the pressure inside. Make sense? Okay. Let's do one more law. It's basically Avogadro's law. Equal volumes of gases at the same temperature and pressure have the same number of molecules. So he figured out that 1 mole is equal to 6.022 times 10 to the 23rd molecules and equal to 22.4 liters at standard pressure. He said V and N are directly related, so he kept pressure and temperature the same. Okay, pressure and temperature has to be the same. So that's why on our mole map, we can only use that 22.4 liters if we're at standard temperature and pressure, because that's when that was done. Okay? So, here we've got a little and that's why we can use that conversion. Okay, so that's the end of the kinetic gas and laws. Practice, practice, practice. Remember all those little tricks that I gave you in all these notes. And we'll see you in your class.